Dear students, welcome to the knowledge series. Here we are going to see two different examples under Dijkstra algorithms to find the shortest path. In this example, you will notice that the link cost between two edges is having a negative weights. So that is the one unique things that you observe in this particular point of our discussions. So let us see how this particular problem is going to solve. So we can put this one as a negative edge. That is the link cost is negative. So how we are going to solve? So let us apply the similar procedures. Step 1. In the step 1, we are going to find all the vertices with respect to the emerging node. So since there is no arrow over here, so we will put certain arrows in this particular network. So let us put some arrows as you are seeing. So similarly for this also we will put an arrow in the similar fashion so that both network appears to be similar. So here by viewing this one, automatically it gives an idea that A is the starting node, A is the start, and it terminates at D. So this is the end point. So here also it's a end point and this is a start point. So looking into the first figure, we will consider that A is the starting point, so all the vertices will be marked with its own weight. So automatically its weight is considered as 2 because its weight is 0, 0 plus 2 is 2. And here only A to B and A to D is considered as a direct path. So automatically here its weight will be 8. Whereas C, it is an indirect path, so its weight will be infinite. Okay. Now based on these conditions, we will be seeing the rest of the things. So step 1 we put as denote weights of all vertices. Step 2. Step 2 case, if you consider among these vertices, B is considered as the shortest path. So shortest path from B. So we will consider with respect to the shortest path BC. So automatically the B weight is 2 plus link cost between B and C is link cost is 3. So we consider it as 3. So automatically it gives 5. So 5 is the weight at C, which is lesser as compared to infinity, So this is a relaxed conditions. So we need to modify this one. So we modify this one as 5. Now next we will consider what the path from C to D. So next shortest path is what? C. Shortest path from C. So we consider CD. What is CD? C is 5 plus link cost is minus 6. So that is minus 1, which is less than 8. So this is again a relaxed conditions. So what we will do, we will modify this one by minus 1. So this is the new weight. So we have seen that it works perfectly. It works perfectly with the negative weight. Although this negative weight it emerge here, but still then it works perfectly, and it has weight as considered as 1. So we got all the 3 weights as one is starting with 0, 2, 5 and minus 1. Now we will apply the similar practice for the second network or second figure, where only the modification was made is that here it was 8. This is replaced by a new modified weight as 1. So only the modification, not we don't consider as a modification, only the figure modification is that only this weight has been changed by 1. So let us start. We will follow the same practice as we did it in the figure 1, the step 1. Step 1 is to assign weights of all vertices. So automatically we will be assigning. From here to direct path is AD and AB. So automatically here it is appeared as 2. Here it will appear as 1 because its weight is 0. And here it will be appear as how much? Because it is an indirect path, its weight will be infinite. So we go with next step 2. Step 2, among these, which is the shortest path, by viewing it, automatically D is the shortest path because its weight is 1. So shortest path is path from D. But there is no edges. There is no edge going out, or there is no link going out of D. Everything is tending towards C. So under this condition, no edge emerge out. So we can ignore it. So this one is ignored it. Now next we go with next. So next we find that B is the shortest path. So shortest path from B. So from B, when we do, so we will look for the path between B and C. So we will say B to C. So B to C is what? Weight of B plus link cost between B and C, that is 3. That is, we got it as 5 at C, which is less than infinity. So it's a relaxed conditions. So in this case, in the relaxed conditions appears means it is modified to 5. Next, we go with shortest path among C and D is what? Amongst C and D, already D we visited. We have only left C, but from C the link is going towards D. So we will find from C to D what is the shortest. So shortest path from remaining node, that remaining vertexes, that is C. So C to D. Let us see what is C. It is 5 plus of minus 6. how much it is? Minus 1. And minus 1 is less than 1. So it is a relax. Now here you see one thing is that previously it was 1. Now it is changing to minus 1. Okay, that is what here you have seen. Here it is minus 1. Now under this particular case, the what you understood is that these vertices at D, it was 1 and later on it was modified to minus 1. That shows that the weight has been relaxed in these particular conditions. And under this particular scenario, in Dijkstra algorithm, once the vertices is modified, it should not go for a further modifications. But because of the negative edge, Dijkstra algorithms find a relaxation condition. And under the negative weight situation, Dijkstra algorithms sometimes fails. These algorithms even find it difficult to give appropriate results. Sometimes it will not work properly. So under these particular situations, because of the negative weights, Dijkstra algorithms need to have a another way to solve, or the network that has a negative weight, if it is not getting solved by Dijkstra algorithm, then the alternate solution is Bellman-Ford algorithms. So we will discuss about Bellman-Ford algorithms next. So this Bellman-Ford algorithm specialty is that it can take the negative weight and based on certain conditions, it will try to iterate it to give a solutions. So here a special figure is being shown with respect to negative weight, and to see that by using a negative weight you find variations in the vertices which was not supposed to modify itself. So with this we come to the end of this numerical problem of Dijkstra's algorithm. Thank you.